Okay, so today I thought we would continue on with our discussion of the Coriolis force. And in the last time, we looked at the Coriolis deflection from an object that was dropped from some height above the Earth at some latitude. And now we really want to take this to the projectile motion level and look at an object that's launched. And we're kind of paraphrasing or borrowing on problem 10.24 from Morin's classical mechanics textbook or problem 9.26 from Taylor's classical mechanics textbook. It's roughly the same idea, the motion of a projectile under the influence of the Coriolis force. Last time we derived, I guess I'll call them the Coriolis equations. This is assuming that we're not including any centrifugal force, or if you want that the centrifugal force has sort of been absorbed into this effective gravitational constant, although even there's a little bit of a directional difference between what direction G truly points and the effective G. But it's order omega squared. And we've already said several times that since Earth is not rotating very quickly, we'll only keep things that are of order omega to the first. These are exact, neglecting the centrifugal force, but the solutions that we're going to develop are always going to be to first order in omega, because if we went to second order, we'd have to include the centrifugal force anyway, and I don't want to do that. So here's the idea. Let's say that we're launching a projectile from some colatitude theta. So remember, that's the angle on the sphere that's down from the North Pole. And for now, let's just say that we're launching it directly to the east. So our coordinates here, x, y, and z, this local Cartesian coordinate system, is going to have the x direction being east in the positive sense, the vertical direction being z, so that's the radial direction on the Earth. And then I'll also go ahead and put in that if this is z and x is, say, into the board, we also have that y will point north. That's to make sure we have a right-handed orthonormal coordinate system. Okay, so just like last time, what we're going to do is we're going to start by using the approximation with no rotation, so the 0th order approximation, which just has that z double dot is minus g and everything else is zeros, to write down our 0th order approximation. But this time I'm not going to set all of the constants to 0. We're not dropping this, we're firing it. So I'm going to leave it generic. So to the order of omega to the 0, we can integrate these equations with omega equals 0, just like we did last time, except I'm keeping all the terms. Okay, and that's the classic one-dimensional or three-dimensional constant acceleration kinematics equations that we know and love, with our acceleration just being minus g in the z direction. As before, I'm now going to substitute these three 0th order approximations back into my Coriolis equations to get a new set of differential equations that I'll now solve to first order in omega. So plugging those in, what will we have? Let's see. Well, y dot and x dot are both just going to be v naught x and v naught y, because there's no acceleration in 0th order. So is that a cosine here? Z dot, however, does have two terms. Okay, so that's maybe a little bit messy for x double dot. All right, for y double dot, not so bad. And then for z double dot, we end up with this. Now notice that aside from this t showing up here, all these extra pieces are just constants. So integrating a couple times will not be too hard. Let's see what that gives us. One integral will give us our new x dot. And of course, we know that when t equals 0, I'm going to get a constant of integration, which I'm just going to immediately write as v naught x. That's still the case. These bits that don't have a t attached will pick up a t. And then what do we have here? A minus minus becomes a plus, and then the integral of t will get a 1/2, which will cancel this down. Okay, so hopefully I did that right. I sort of distributed out, or I didn't distribute, I factored out the pieces that are completely constant. We should kind of remember this is a subscript here. Integrated once there, and then we get this extra piece, which will have a quadratic term. These two are going to be basically the same thing times t. Okay, so not so bad for the derivatives. And then finally, one more integral will give us the positions as a function of time. It's going to be a little messy, but again, everything here is constants except for the t's, t squareds that show up in each of these. So just power law. Phew, okay, I think that's everything. So our x position, remember this is the east-west direction that we're determining here, which we're very interested in. Has some starting position, some initial velocity we kind of expect. This whole term, which has a t squared attached to it, that's proportional to omega, so this is new, it's a Coriolis effect. And this cubic term also has an omega in it, which also gives us a new effect that's kind of interesting. You could even say that since there's a cubic term here, effectively there's a jerk. In other words, if I took 3 derivatives, so I went all the way back to this and took one more time derivative, we can see that the jerk in the east-west direction is non-zero. And then in the y and z direction, we get kind of the constant acceleration feelings that we would normally get that have a t squared component, although notice both of those do have an omega piece to it. Z also, of course, has the g that we would see normally. Okay, now we're going to specialize to the particular case of launching this projectile at some velocity in some particular direction. I'm going to call the angle of launch above the horizontal alpha here, because unfortunately theta has been taken by our polar angle. And our goal here is now, let's see which of these things simplify down in that case. And remember, I'm launching it directly to the east. You could leave this quite general and leave all the v naught x's and y's and z's, but I'm going to choose coordinates so that I'm starting at the origin. I'm just going to choose my local origin to be the launch point. And since I'm launching it to the east, v naught y is actually 0. I'm not launching it with a northward or southward component. So here and here, those go away. And then all I'm left with are v naught x's and v naught z's. But of course, those are going to be written in terms of v naughts and sines and cosines of alpha. So let's go ahead, let's bring this to the top, and I'll go ahead and plug in the v naught x component, which will be the horizontal, that's cosine alpha, and the v naught z component, which will have a sine alpha. So let's see what that looks like. Okay, so here are our slightly simplified equations for east-west, north-south, and vertical for this launch occurring towards the east from the origin. Now, there's a couple things we are interested in finding. First off, we're going to be interested in the deflection. So how much is it deflected east-west or north-south, etc., due to this Coriolis effect. But there's a few other things that are probably interesting to us also. For example, what's the flight time? Okay, we might want to know how long is it in the air. So that's solved from using our z equation. Again, we're assuming that the curvature of the Earth is very, very small. In other words, the radius of the Earth is large. So we are looking for when this z comes back down to 0. And setting z of t equal to 0, maybe I'll call it z of capital T equal to 0, we can see that we have a t in each of these terms. So obviously when t equals 0, it's on the ground because that's the launch point. I'm interested in the non-trivial solution here. And so I'll just go ahead and set 0, factor a t out of all of this. or cancel a t out of all of these. And then let's see, the easiest way is probably, let's subtract, and I'll find a common factor here. Let's call this capital T. Okay. So this is the equation that'll give us our time in the air. When I move this over and divide, it'll look a little funny, but we'll clean it up in a sec. Let's try to rewrite this in terms of the non-deflected or non-rotating flight time, which we already know are 2 v0 sine alpha over g. So I'll write that as 2 v0 sine alpha over g, factoring this basically out of the denominator. And what I'll be left with here, I'll have a 2 omega v0 over g, and then some trig stuff. Now, as it is, that's fine, but since we're working to first order in omega, let's go ahead and use the binomial approximation. This is 1 minus something small to the negative 1 power, and as a reminder, 1 plus any small thing to a power, at least to first order, is basically 1 plus that power times the small thing. And for us, the power is negative 1. And the small thing is all this with the negative sign, so the negative will cancel. So I'm going to rewrite this as approximately T naught, that's this thing right here. That's the flight time when there's no Coriolis deflection. And then I'll write this as 1 plus my small thing. So we can see a couple things. First off, the flight time is a tiny bit longer. I'm adding a little positive number to this 1, multiplying the original flight time. And so that's telling me that due to the Coriolis effect, this will be in the air a little bit longer. So maybe we're kind of expecting the range to be a little longer or something like that, or the path taken to be a little longer. So that's the first thing we have. Secondly, we can see that we get a new little dimensionless number here, omega v0 over g. That has to remain small, so we're not really launching this at extremely high velocities, or else maybe this term really should stay in the denominator like this, and we might need to worry about those omega squared terms that we've been trying to avoid. Next thing we want to do is take this and plug it into y to find out how much the deflection is. So I'll put a little star here as one of our interesting facts. Here's another one. Y at this landing point is no longer 0. In other words, I might have imagined firing this directly to the east and it'll land somewhere directly east of where I fired it, but now we're going to see that's not true. In fact, plugging in t for this thing, at least to this order, gives us something a little interesting. First of all, the whole thing is negative, which means y, remember that's north-south, will be deflected to the south. So firing this directly east, it actually veers a little bit to the south. That's kind of interesting. We're really kind of expecting that for Coriolis-type deflections. There will generally be a deflection in an orientation that gives rise to things like the motion of hurricanes, things like that. Only on very large scales, though. And actually, since I'm doing everything to first order in omega here, I should probably just neglect this second term, because when I square this out, I'll have omega squareds. Or even if I have a linear term in omega, it'll multiply this other linear term in omega. And I only want to keep omega to the first power to be consistent. So I'm just going to write this as negative. I'll leave T naught as is. Something that depends on the launch angle and the altitude, and the latitude, co-latitude. Again, the negative sign means this will be deflected south by a bit. Okay, so that's kind of interesting too. And if you want, we could plug in some reasonable numbers for V naught, maybe pick a 45-degree launch angle, something like that. You'll find that this is not a terribly large amount for reasonable amounts of V, but it could be reasonable to include this if we're doing things with very high muzzle velocity, say howitzer firing or something like that. For example, in World War I, there was a very large cannon. What was it called? Probably should look that up. I want to say Big Bertha, but I don't think that's it. It was a German artillery cannon that was actually going to be used to shell Paris from a distance of 100 miles or something insane like that. And the idea being they could have this well behind enemy lines and still be able to shell enemy cities. So imagine, a Volkswagen Bug-sized shell basically coming out of nowhere from 100 miles away. You wouldn't even hear the cannon fire, and landing, blowing up a block or something. They never really did get close enough or use it effectively, thankfully. But when they actually were doing calculations here, they did have to include the Coriolis deflection that would occur when they're talking about their ballistics, because that's a big enough distance and hence a high enough velocity that this term is certainly not negligible. Finally, let's go look at X. So in other words, what's the range, right? We've been calling this capital R for the range of this projectile for a long time. It's the position when this lands. Probably would have written it over here as R. Well, okay, I'm going to plug this whole thing in. Now I have a t here, a t squared here, and a t cubed here. I'm only going to keep first order because you can see that this is going to get pretty ugly pretty fast. But if I only keep first order in omega, I'll plug the whole thing in here because that'll have an omega. I'll only plug in the t naught here because the omega there will give me higher order for the other terms. Same thing for t cubed here. Whew, that's long. Okay, well, let's do a little bit of algebra to clean this all up. Okay, so I went ahead and did that for you. It's a little annoying to have to write that all out. The t naught, don't forget, is this whole bit here. I did go ahead and expand that out a little bit so that we could see the part we were expecting when there's no rotation. So this is the normal range formula. You can recognize I used a double angle formula there. And then here's all the bit that came from omega. And I'm missing one thing here. Sine theta, notice, shows up in all of those terms. Does depend on the latitude, okay? Co-latitude. So notice that, okay, we have our usual range formula, a positive number. This thing has a minus sign, so we are kind of wondering, will this end up giving you a slightly longer range or a slightly shorter range? Does it matter? So we'll think about that in a sec. But notice that this correction term depends on the cube of the launch velocity. So it is highly dependent on that launch speed, but of course it also shows up with that omega, which is a small number for things like the Earth. And then this rather complicated dependence on the launch angle alpha. Okay, and then finally, let's think a little bit about this extra term. In other words, is the eastward or westward deflection, which is this whole piece here, well, is it eastward or is it westward, or does it depend on your launch angle? Well, let's see. Notice that there's a sine alpha I can pull out of both of these terms, and I'll be left with a cosine squared alpha minus 1/3 sine squared alpha if I do that. But of course, we could rewrite that a little bit with something like the Pythagorean identity. Maybe I'll go ahead and do that up to the side here. So this thing, which I'm underlining in red, is the same as this. Let's use our Pythagorean identity to replace cosine, say, with 1 minus sine squared. And then combine those together. So we can see that There are some values of alpha that will give me a negative number there. For instance, if I just set this equal to 0, I'd have that sine squared alpha is 3/4, or if you prefer, sine alpha is √3/2. We're dealing with positive launch angles here. And of course, we know what satisfies that. That's a 60-degree launch angle. So what that's telling us is if you're launching your projectile, independent of latitude, by the way, if you're launching your projectile at an angle greater than 60 degrees, this term here will be negative, which means it's actually going to be deflected to the west. And if you launch it at something less than 60 degrees, then that will be an eastward or positive deflection. And if you launch it directly at 60 degrees, this whole second term is 0, which means there's no difference between the range of the rotating versus the non-rotating sphere. This kind of tracks because we can imagine if we fired it directly up, okay, as the Earth rotates beneath it, it will end up kind of falling back down to the west or behind where it had initially been launched. And that makes sense. If I do plug in, say, alpha equals pi/2, this part is 1, this part is 0, I definitely have a negative number there. And in fact, that third that comes out here could also show us the amount of deflection from a vertical path, just like we saw last time. The only difference here is we're going up and then back down. We're not dropping it from some height. So the prefactor here will be off by, I think, a factor of 2. At any rate, we've pretty well analyzed the motion of a projectile under the at least first order influence of the Coriolis force, and we found its deflections both to the south in general, as well as to the east or west. QED.